Module 4 is, in my opinion, the most fun. Also tends to be the scariest for people coming into programming in general. So for those of you who have, say, coming into this with experience in other languages, you know, class development or writing classes and data types is perhaps something that's familiar to you, at least in principle. For others who are just coming at this, you know, totally from scratch, this can be a little strange to think about at times. But this module will focus on designing custom types. We've been, say, working with our ints, integers. We've been working with our floats, our lists and other sequences, and now our dictionaries. They you know, have methods that are defined on them, like extend for lists or pop for both dictionaries and lists. And there are definitions that define those. Int and float and list and dictionary, those are classes. They have class definitions, and those class definitions define those types, defines the methods that we can use, like extend defines what happens when, say, we call len, L-E-N, len, on, say, a dictionary. The specification of what describes those behaviors, all of those methods that are available to us and those attributes, they're available to us as well to be able to design our own types, which, as you'll find this coming week in the CompuCell workshop, is incredibly useful for a number of applications. In our case, very useful for being able to generate models that are compatible with the simulator. The notion of designing custom classes is leveraged in CompuCell and is at the very core of model specification using Python. And for as maybe abstract as that may sound to some people, it actually generates a way for us to be able to do rather complicated things in a very simple way. And so we're going to explore some very basic aspects of that now, so that in this coming week, when we go to actually do this stuff in Python for CompuCell, some of the ideas might not be you know, so foreign. So we're going to talk about classes. And when we talk about classes, we have to make this distinction between, and maybe this is a working concept now for everyone, which is great. But the distinction here is important to make, that you know, we talk about things like types, ints, floats, strings, versus objects. And you know, when we've been doing all of these little test scripts, A equals 1, B equals, you know, a list, so on and so forth, every time that we instantiate something, what we've created is an object. And that object has data on your computer or on a server if you're using NanoHub. And the data that corresponds to that object is according to its type. And the type defines not only the data that makes up an object, but also defines the ways in which that object can be interacted with. For example, extend, pop, append, remove. All of those methods defined on list, all part of the class definition that defines the list type. And we can create lots of instances of, say, lists or bools, but all of them are the same type. They all have the same methods. They may have different underlying data. You can have ints lots of ints with lots of different values, but every int will have the same operators defined for it, and so on and so forth. So object versus type. Every object is an instance of some type. All right. So with that distinction, I just talked through like 5 of my slides. That's fine. Got an example here prepared that probably the point is already well made. So the thing about defining classes, and I don't want to get very much into this because in this coming week, we will do a little bit of actual design of classes, and that we can define the way that data is stored in our models. When we implement models in CompuCell, we'll have data that we'll be interested in, and we'll be interested in storing it in different ways and performing different types of typical manipulations on it, and so on and so forth. And we'll do that through methods that are defined through class definition. And so it's important here to think at least a little bit about that. Part of the sort of worldview of class design is to define what types of actual underlying data make up a class or an instance of a class, and then think about the methods that are presented for operations on those instances, and how those operations actually affect the underlying data. And as an example, you think of that we've been creating lists of different elements, and those are ordered. And you can ask the question, why is a list order specific, but a dictionary isn't? And of course, the obvious example is because the person who designed the list designed it to be order specific, and vice versa for the case of the dictionary. But in the actual implementation, and this will be important to some extent when we actually go to do our CompuCell Python, is that there are corresponding types of operations that are defined on the class that make those properties available. Like in the case of the list, having the data having a specific order. All of these different methods, they all operate around this sort of internal representation for the case of the list, that for every element in the list, there is a reference to the next element in the list. And that referencing scheme is what makes a list ordered. We can do similar things for whatever sorts of things we may want to implement in our models when we do CompuCell models. But what's important here to recognize is that there are internal calculations that will occur for instances of a type that make the sort of available methods and calculations both available and happen. And so with all of that ado out of the way, let's just go here for a second, and then we're gonna actually do a little bit of coding. So one of the probably most complicated parts of working with classes, and I also only bring this up because we will use it this coming week. Every time we use anything CompuCell Python, this notion will come up from pretty much day one, is the idea of class hierarchies and what's called inheritance. And that is to say that for every class that we may design, for every, say, custom type that we're going to create, what we can do is base the definition of a class on a definition of another class. In that, if I have, say, something like an existing class definition for an animal with methods on it, like where is it, or is it asleep, or I don't know, is it on Earth? it's then possible to take that class definition for an animal and use it as what's called a parent class, or some people call it a superclass, and write a new definition for a class based on that parent class, such that what's called the child class, the class that inherits from the parent class, gets all of the definitions that are defined for the parent class on it, and then can add more things. So if my, say, animal class definition has a function defined on it that tells me whether or not an instance of the animal is on Earth or on Mars, when I inherit that class definition when defining some new class called person, I automatically get that function on Earth, on Mars, whatever, defined on my person class, or say a cat class or rabbit, and so on and so forth. So there's this notion of inheriting these abstract ideas from a parent class to a child class, such that we can sort of abstract away a lot of the things that either are very basic across, say, a modeling platform that we may be interested in building, and then can sort of like template out that functionality onto particular instances. We do this a lot in some of the research that we do in CompuCell, but at its very heart, we do this every day with building CompuCell Python models in general. We get a lot of practice on this throughout the week. So, but what I would like to do is sort of get that idea into everyone's head now who may not be necessarily familiar with it. And maybe it'll be a little more clear when we actually go to design our first class. So let's make a class. I'm going to split my screen here. Again, don't worry if you didn't get this function from the end of module 3. Some code will be provided as well as the slides for your reference. Let's make a class. So defining a class has some of the same procedures as defining a function, except that a function is just a function. We can call it, we can get something from it, we pass things into it. Whereas with a class, we're actually using this as a prototype to create things in data, potentially lots of instances of a type in the actual memory of our computer. So, but we're going to start it similarly to how we start a definition, and that is that the class also has a header, and that header begins with the keyword, maybe you guessed it, class. And the name that we would like to assign to our class is specified next. We use just a simple example here of defining something like a coordinate. Say a 2D coordinate. So let's call our new class coordinate. I like this example because you think of coordinates in, say, two-dimensional Cartesian space, something like a vector. You have something like an x coordinate and a y coordinate, and the combination of those two describes a coordinate. We're going to create a custom class that represents that idea. Now, if we have a parent class that we would like to inherit from, we can specify the parent class after the name of the class that we're developing, and we name the parent class in parentheses. Now, in this example here on the right, and I'm going to follow this as we go through it as well, what's shown here is that this class coordinate is inheriting from a class called object. But you'll notice if you refer to my screen that object is shaded in the same color as like what you see for len or dir or for the string constructor. And that's because object is a built-in class in Python. And in fact, object is the base, like the ultimate parent class of all classes. That it's possible to have this sprawling hierarchy of an infinite number of layers of classes inheriting from more classes and more classes than you could possibly get your head around. But what you will find is that when you trace your way up the hierarchy, eventually you'll find that something is the child of object. And hence in Python 3, this declaration is actually not necessary. So if not inheriting from something else, the assumption is made without this declaration that one would like to inherit from the object class. But we'll write it here just to get the practice of writing something like inheriting from a parent class. Now, after we finish our header, we can terminate it with a colon, and then like the function definition, we'll start the class body, and that will consist of returning one line and then starting a new level of indentation. So this is like the defining the class body. Everything that's within one level of indentation will be considered as part of the class body until 2 lines are found at the original level of indentation at which the class definition began. And now we're gonna give some personality, and by that I mean some characteristics or what are called attributes as well as methods to our coordinate class. And so to begin, there are specifically 2 things about classes that are intrinsic to their definitions. The first being simpler of the 2, I think, maybe the more complicated, I guess depends on who you ask. But the first type of object feature, I guess would be the word. The first type of feature that belongs to a class definition is what's called an attribute. And an attribute is data that belongs to an instance of the class. And by that, what I mean is that we can assign data like, say, an x coordinate, a y coordinate. We can assign that internal data as attributes to every instance of our coordinate class. And for every instance that we create, each will have underlying data that corresponds to the attributes that we define on the class definition. So that's the first type of feature for coordinates. And there's no limit on how many attributes you give to a class. The only limit is that they must be uniquely named for the class. Just like overriding the name of a variable, the same is true for defining attributes for a class. And we'll go through how to actually do that here in a second. But secondly, the second characteristic feature of a class is a method. And a method is like a function, except, maybe you guessed it, a method is a function defined on a class, like append for list. So all of the functions that are made available to us that are defined on all the types that we've worked with so far, those are implemented as what are called methods. And from our experience, we know that we can take an instance of some type, and then after referring to its name and then typing a dot, then we can refer to the methods like append or pop. So we can do that on the basis of individual instances of a particular class. There is a lot more to this, and we're going to neglect it for now. However, if you are interested in knowing more about this, there are actually lots of there's a whole variety of methods that you can define for classes. So if you'd like to know more about that, there's a whole variety of actually both attributes and methods. And I'd be happy to provide some resources to those of you who may be interested in some of those details. But for now, let's start by defining how to, well, let's figure out how to describe what happens when an instance of our class is created. What's a part of every class definition is a set of descriptors for basically instructions for what to do during certain operations on our class, like creating an instance of it. So when we have been doing things like x equals list, there are instructions to describe what happens when a list is created. And we can do that for our class as well. And we can do that with a specially named function called init, where init is both preceded by and followed by 2 underscores. You see my IDE will highlight it or show it as hot pink or magenta, depending on how easy color. And it's highlighted as such because it's very special. And it's special because this is the function that will be called when an instance of our class is created. Underscore, underscore, init, underscore, underscore. And init, like all typical methods on a class, will always take an argument as its first argument that is also very special. And you see my IDE will populate the argument automatically for me, and that very special argument is called self. Now, we didn't cover this much, if at all, when we were going through functions in the previous module, but you can see an example of it here. You can specify an arbitrary number of arguments for functions just by using a comma-separated list. So something that looks like a tuple. It's not a tuple. Just everything that I name in a comma-separated list, each of these are arguments that would be passed into, in this case, the actual constructor of my type in general. But for now, let's just keep it very simple and deal with this idea of self. And again, self will be the first argument in every method, excluding the variety of methods available that we won't deal with today, or really much this week that I can think of. Outside of our self argument, which we'll address in a second, let's say that to create one of our coordinate types, if we say we're talking about 2-dimensional space for our coordinate, let's say that to create a coordinate, one has to give an x and y value, those corresponding to, say, an x or a coordinate along an x-axis and then a corresponding coordinate along a y-axis. And what we'd like to do is have our coordinate class have underlying data that consists of those x and y coordinates. And so how do we attach these values that are given during the creation of a coordinate? How do we store that in an instance of a coordinate class? Because again, we can create lots and lots of instances of coordinates, and we need to, provide instructions for how to store these x and y values for every instance of a coordinate class. And we can do that with self. Self, in every typical class method that we'll deal with, self is a reference to an instance of this class. In that when I say something like self.x equals x, x being the argument that was passed into my init function, self being this very special and sometimes mysterious for some argument that's passed as the first argument. When I say self.x, what I mean is that when doing instructions on an instance of my coordinate class, self refers to the instance for which the instructions are being carried out. And so when I do something like, say, C1 equals coordinate, and I pass 0 and 1, this is creating a coordinate, an instance of my coordinate class. What's happening here is that when this instance C1 is being created in the first place, a value of 0 is being passed to the named argument x in the init function, and that value of 0 is being stored as an attribute for the C1 instance, and it's being stored with the name x. In which case now what I can do is things like maybe what we've done a little bit already throughout the day, and that is I can refer to this named attribute x because it was defined on the coordinate class as an attribute using this declaration. When in the init function I say self.x equals something, that automatically adds an attribute named x to every instance of my coordinate class, in which case I can say print c1.x. And when I do that, I get a 0. 0 was passed to the named argument x, which was stored as a named attribute with the name of x on an instance that was created, and I can refer to that with the same name. You'll notice that my IDE even highlights the attribute within the init function. C1.x gets highlighted for self.x because self refers to whatever instance is being operated on. And so likewise, we can also say self.y equals y, and you guessed it, print c1.x and c1.y. I get 0 and 1. Specifying attributes on a class is as simple as that. Question about these coordinates. Self could be a geographical location or a specific location in a blood vessel. Absolutely. And in fact, doing that sort of abstraction with classes, I would say is one of the most powerful applications of using class definitions and class design. So if we're all good there, I often find that people find this elusively simple in the sense that this creation of attributes by just simply declaring them on this self variable, it almost seems like there's not enough work involved. Or that something else needs to occur. but quite literally declaring these attributes on self in the init function automatically does this for every instance of our class that's created. And we're not restricted to declaring, only attributes that say correspond to things that have been passed. We can just make up nonsense if we want to. Self.garbage equals none. Doesn't mean anything, but now coordinate has an attribute called garbage. And when the class is, or when an instance is created, the attribute of garbage will be initialized is equal to none. Simple as that. And question, so in this example, C1 is within the definition of self. So when C1 is being created during this call, self is referring to C1. So I think I want to answer your question as yes. If, for example, I say C2 equals coordinate, and then say 1 and 2, then here at line 7, when coordinate is being called here, passing 0 and 1, self, when doing line 7, self refers to C1. And when doing line 9, passing 1 and 2, x and y equals 1 and 2, when carrying out line 9, self refers to C2. These are instructions that are carried out on every instance of coordinate. And concerning what's the null, that be in reference to my silly example of creating additional attributes. Because if so, this is only to demonstrate that creating attributes on classes is as simple as declaring them on self in the init function. You can do this other ways, but I'm not going to talk about it because I don't recommend it. Best way to declare an attribute on a class instance is in the init function by just saying self dot and then naming the attribute and then assigning it some value. A couple more questions in the chat, all of which are spoilers on the exercises that I have planned, so that's great news. And in fact, yes, the question about calculating the norm and so on and so forth, yes, absolutely. So defining methods on a class is how we do this. How we do, say, things like defining a norm method on a coordinate such that every time we call norm on one of our instances, it'll automatically calculate the norm of our coordinate based on, we've been saying it's internal data, in this case, based on the values of the attributes x and y. So let's do it. And in this case, let's write our first actual method for doing some calculations and for writing methods on classes. We define these in general in the same way as we defined functions, with the following two rules. First, as you see here in the init function, but now explicitly stated, when declaring the header of a class method, we do start with def, as in with normal methods, but again, while respecting the level of indentation of the class body. So again, everything one level of indentation up from the class header is considered part of the class body. And so in this case, if I say had def here, def my function, this is a function all on its own, whereas this is a method defined for the coordinate class. And so in this case, let's name our function distance, just like we would with any old function. And let's go ahead and start some parentheses to specify some arguments. And you'll notice with my IDE, if you're watching, my IDE will automatically, again, populate this method with the argument self. And that is because every class method can refer to itself. When we do things like call self dot or say pop or remove or append on a list, each of those has a class method that refers to itself when carrying out whatever is defined for that particular method. And the reason that this is powerful is because when using self to refer to, just like in the init function, to refer to whatever the internal data is for a particular instance of this coordinate, the particularities of the instance is totally abstracted away. And instead, all we're thinking about here is not necessarily what an instance of the class, what its state is, but rather in general, what is the distance from, say, one instance of our coordinate to, say, another instance of our coordinate, without regard to the actual values, but just in terms of every coordinate has the attributes x and y. We only have to think in those terms. And so if we want to say, define a method called distance on our coordinate object, and all of this function does is just takes as argument some other coordinate instance and returns the distance from itself to the other coordinate, we can do something like as follows. Say dx, call it dx2, which would be the square distance along the x coordinate. And let's do parentheses. We're going to refer to the x attribute of the instance of this class, whatever instance it is, the one that's called when someone is using our class. It's referred to this instance's x attribute, self.x. And while we're at it, if we're going to compute the square distance along the x-axis of whatever coordinate system this refers to, we can just say in our parentheses self.x minus other.x, assuming that other refers to some other instance of our coordinate class. And then square it. Now, if you're struggling with this concept for a second, just bear with me, follow along, and then we'll talk through this within the context of actual usage, and then maybe it'll be more clear. So for now, hang with me if you're struggling. Let's compute the rest of this. Let's fulfill this method definition, and then let's actually talk through this and see how this magic is happening. Let's do the square distance along some y-axis. We'll call that dy2 equals, and we'll say self.y, referring to the y attribute of this coordinate instance. And we'll subtract the value of the y attribute of some other coordinate, which is passed to this function as an argument. And then you guessed it, we'll square it. And then let's do distance here by returning. And we'll do our squared distance along the x direction plus our squared distance along the y direction, and use the power operator to take the power of 0.5 to the square root. So this question, how is instance defined? So yeah, in the case of computer science, excuse me, so we have this distinction between the type of an object and an instance of a type, in that we are here defining a class, which is the definition of a type, and then we can create objects that consist of instances of that type. So C1 is an instance of the coordinate type, as is C2. Both are instances of the same type, but they are different objects. They may be instances of the same type, but each of them has a place in memory. In this case, each of them has the attributes X and Y. They can have instance equals object type. No, instance is an object of a particular type. Maybe we're saying the same thing. I just want to make sure that we're clear. You know, so like, for example, did a lot of A equals 1, B equals 2. A and B are both instances of the int type. C1 and C2 are both instances of the coordinate type, and A, B, C1, and C2 are all objects. So an instance of a type is an object of that type. And maybe it seems a little pedantic, which I try to not do unless absolutely necessary. But in the case of you know, relating the, you know, what occurs in the definition of a class compared to how it's actually used, I tend to err on the careful side when it comes to the actual terminology that's being used. And maybe that'll be apparent here. So for those of you who stuck it out with me and defined this definition of a distance on this coordinate class, maybe some of you guessed it, but now I can come down here and for one of my coordinate instances, C1 or C2, I can say C1 dot distance. My IDE recognizes it. And what I don't pass is something for self. This is maybe the most confusing thing, the most, but the easiest way for people to get tripped up on how to actually implement class definitions, because there is this argument here for this class method, for init and for distance. Both of these methods have the self argument. And yet, if C1 in this case is what's referred to by self, the natural question is, should I pass C1 as the first argument if I want self to refer to C1? Which is reasonable, except that what occurs here actually under the hood is that Python will automatically, without any intervention on your part, actually with the assumption that you won't do anything regarding this, Python will automatically interpret this as C1 being passed to the argument self. In which case, the first argument that we pass in this call will actually be the second argument that's passed to the method. The instance that is called will automatically be passed to self, and then all of the arguments with order respected will be passed as arguments after that. In which case, if I say C1.distance and passing C2, C1 is self in this case. When executing this instruction, C1 is self and C2 is other. In which case, maybe it's a little trivial now to see that both C1 and C2 are coordinate instances, which means they both have the attributes X and Y. In which case, if C1 is self and C2 is other, then we're just doing C1 minus X, or C1, its attribute value for X minus C2's value for X squared, same for Y, and then returning the square root of the sum of those distances. And when reversing the call, C2 dot distance of C1, when carrying out the instructions for line 17, now C2, which is a coordinate instance, C2 is what's passed in as self, and C1 is now other, because both of them, being coordinate instances, have that method defined. Now let's do a poll again and see how we're doing with this. Because if we're gonna lose people, maybe this is the spot where it might happen, and I just want to make sure that it's at the end of the day and it's a fairly abstract concept, and so just want to make sure that we're at least on the same planet here. All right. While we're giving everyone time, Maria asks, is it possible to generate a list of these classes? You betcha, you sure can. Class instances, just like ints and floats and everything else, they can be in lists, they can be in tuples, they can be in dictionaries, subject to the constraint that I mostly glossed over in our last module about the consideration of whether or not an instance is hashable. And we're not going to deal with that this week. So we're just going to neglect it for now. But in general, yeah, you can do my coordinates, say, is a list, and then for n in range of 10, and just say my chords and just append instances, say n and n plus 1, iterating from 0 up to 9 inclusive, and just creating a coordinate with the x value equal to n and a y value equal to n.1. That's created here, and then it's automatically appended to this list my chords. Similar operations for dictionaries, as we sort of crashed through in our last module. All of that is relevant to working with these custom class types. And maybe this seems a little off the deep end for some. So for those of you who may feel like this might be a little too computer science-y. This is one of the most useful things for biological modeling, in that the class definitions that we write for CompuCell are how we implement things like a cell definition. Diffusion fields, simulators. Just about everything is formalized in some sort of class definition like this. One, to be able to organize the data well, and two, to be able to present something to users in an intuitive way. We just gave you a list with a bunch of like floats and strings with no coherent structure to it, then it would be pretty hard to work with. Whereas we can write, say, a class definition called cell and give it an attribute called volume. Now, that's not so random. That has some actual meaning to it. And that's what this is getting at, is that lots of the objects that we'll work with in this coming week is all defined in this same sort of paradigm, where the different objects that we work with, like cells or fields, they'll have attributes and they'll have methods defined on them, some of which can be used to interact with the simulation, some of which is used for the simulator to be able to report information back to you. So if you're struggling to see the relevance here because it is a bit abstract, I totally get that, and that's totally understandable. But maybe by the end of this coming week, maybe the relevance will hopefully be a little more obvious. Yeah, so with that in mind, you can do exercises like you know, what I was just kind of typing through here, while giving everyone a chance to work through this, creating 2 instances, and you see calling the same method distance that we defined for our class, but we're calling it on different instances of that class, C1 and C2, and passing, you know, the other instance in this case. And so let's power on and work with this a little bit more. And yeah. And let's do some other useful things concerning class definitions, in particular, how to define interactions for some built-in methods, like when we would call print on an integer, or say when we would call len on a list. There are special methods that we can define on a class that will tell Python how to respond to certain operations that are built in. And so in probably the simplest case, if we would like to say define, and we do this, to define what happens when we call, say, string on one of our coordinate instances, or if I try to say print one of my coordinate instances, print C1, and I get something here that mostly seems non-informative. Tells me the type of the instance and gives me some information about where it is in memory, but by and large, not very intuitive, not very helpful, you know, for just basic usage. And so we can define another special function like init that will tell Python how to respond when, say, print is called on an instance of our class. We have lots of special built-in methods like this for some of the class definitions that we'll use this coming week. So in this case, if we want to tell Python what to do when string is called or when print is called, we can do this by defining a special method like init called str with, again, underscores before and after str. And this is a special method that takes only the argument of self, same self as every other method. It's referring to an instance. And we can do, say, the generation of some custom string based on the internal data of our class instance, and then return a string that reports that. We want to know, say, when we print a coordinate instance, what the actual values of x and y are, then we can here return a string that states what those values are. So we can do something like return and say str of self.x. This referring to the value of the attribute x on this particular instance when it's called. Say str of self.x, and again we can create strings from strings by using the plus operator or the addition operator. Say plus and then a string with a comma separating the string of self.x from the string of self.y. This is just instructions to tell Python what to do when someone calls str, like what we're doing here, calling string on self.x. That's only possible because this special method is defined for whatever data type, whether it be an int or a float, whatever type self.x may be. And we're going to make it possible for the coordinate class as well. So if you want to get fancy and make this maybe a little bit nicer, you can also say add some parentheses around the string that's generated. Expand my screen for just a moment so we can see everything that's going on here. And now I'm going to return to this call to print on an instance of a coordinate, and let's see what happens now. Again, it's implied here that C1 is converted to a string, and print does that automatically. And we'll find here that now when we print the instance of a coordinate, now we get this nice string that is just what's returned by this function. Now there's a lot of built-in methods like this that can define all sorts of operators for particular types. When we've done things like we consider the difference between adding two floats and adding two lists. In both cases, we can take two named variables and type a plus between them. And if they're two floats, then what's returned is the arithmetic summation of the two elements. Whereas if we say have two lists and we say one list plus another list, it's a totally different operation. And the operation being that the one list is added to the end of the other. And those operations can vary using the same symbols, just depending on what the types are involved in the operation. And for classes, this is all implemented using special built-in functions like what we did with str, but also doing instructions like telling Python what to do if, say, we wanted to add two coordinates. What does that mean? And of course, it means whatever the designer of the coordinate class says it does. But what's important here to recognize is that plus, minus, doing comparison operators, or taking len for different instances of different types can mean a lot of different things. And usually in these cases, we refer to documentation if using, say, CompuCell. You know, what did I or one of my predecessors or one of my colleagues define as being an len operator on a class? And these things are designed specifically to facilitate using these different types of abstractions for, say, doing things like what was mentioned in the chat. I say, like, defining coordinates within a blood vessel or something like that. And so as a last little exercise, and I would actually like to, yeah, let's go ahead and get that poll going, and I'll give everyone a couple of minutes to sort of get their head around this, make sure we're good with this. We can just skip doing some of these other built-in methods. I think that we can build some familiarity with that as we go throughout the week coming up. Or again, of course, if anyone's interested in learning some of the more, you know, more of these details, I'd be more than happy to provide some resources for that and get you started in that direction. Great. I see comments in the chat about more details. It's music to the ears of a developer. Now it looks like we have a couple of responses of people who need help. And this seems like a persistent response lately. And what I'm afraid of is that maybe some people are just not following and not getting the help that they need. And so please, if you do need assistance with something, either reach out to one of us in private chat or raise your hand. We want to make sure that no one gets lost along the way, especially in this these last few minutes. Give everyone another minute or so. And we're going to look at our last little bit. And then finish out with some question time. See, there's an issue with getting an error on str and coordinate. Oh, sorry about that. Yeah, so the important thing to note here is that when defining, say, the string method, and every built-in method like this has particular requirements, specifically because you're telling Python ways to interact with your class in a sort of standard way. In this case, for str, nothing gets passed to the function except self, which is done implicitly, and the only thing that can be returned is a string. All right. So in the last 10 minutes, I'm going to do just a very quick little crash course since we have very little time left. There are some, I would say, standard packages depending on the application that you might be interested in. It's pretty much guaranteed that this week you'll get at least some exposure to a couple of packages that get used a lot in CompuCell, one of them being NumPy, which is used in just about, I don't want to say every scientific computing application, but it's extremely common. which is used for mathematics, matrix operations, a lot of things to do with scientific computing. And another package called SciPy, which has a lot of, it's a great library with a lot of features, from everything to do with statistical analysis to optimization, all sorts of things. I've worked with those libraries for a while, and I still don't know everything about them. And so what my hope is for these last few minutes is to actually do a sort of crash course on some useful built-in features that are provided within the Python library, and more so get acclimated to using functions that are defined in other libraries, so that when we actually get to application time this coming week, it won't be such a foreign idea to say get a function from NumPy or from SciPy, import them into a script and start using them according to the documentation. So there are some standards for NumPy and SciPy. And for those of you who might be interested in learning about those between now and tomorrow, I can post a couple of walkthroughs for sort of crash courses on using NumPy. But for now, we're going to look at just some standards. So these are all built-in libraries that come with Python in particular. We do a lot of work with stochastic processes, lots of random number generating, and so on and so forth. And so for doing these sorts of operations, the go-to library, which you can import into your script, is just called random. And you can get this by just saying at the top of your script, import random. And now all of these functions are available. These are just a few, the ones that I tend to see used the most in CompuCell-based modeling. So if, say, I want to get a uniformly distributed random variable in 0 and 1, I can say my randnum equals random.random. Now you'll notice here that I'm actually referring to the module that was imported in a similar way to how referring to methods on coordinate instances, and that's intentional. And that is to handle specifically cases like, what if, say, I had something else named random as well? How would I handle things like name clashes? Two libraries define functions with the same name. How do I use both of them in the same script? And the way that we can do this is through this sort of naming convention. So here, just calling the random function defined in the random module. And if you go and look in the documentation, you'll find that this function will return a random number in 0 and 1 according to a uniform distribution. And of course, you can follow along with the rest of these as denoted here. In particular, I would also like to bring to your attention for this module, for those of you who have not ever worked with pseudo-random number generators, these are not random numbers in a true sense, but they are pseudo-random. So they are predictable, and they are predictable according to what's called a seed. And the seed is what's used to generate the pseudo-random sequence of numbers that can be generated upon successive calls to functions like random.random. Most importantly, if you provide to the random module, if you provide the same seed value to this function seed, and then call functions like random.random successively, you will get the same sequence. This is a repeatable set of floats or integers or what have you that you may be generating. but this is particularly important for generating stochastic simulations in a reproducible way, because if, say, we go to do some CompuCell simulations, and your simulation does something interesting, and then you may run it again and find that it does something different the second time. The way to reproduce something that you've observed in a particular simulation is to use the same random seed, because the same random seed will produce the same stream of pseudo-random numbers. So to make your simulation reproducible, you can declare a seed and then pass it to random.seed. There's a way to respect that in CompuCell as well, and we can get into the details of that in the upcoming week. Same principle applies for CompuCell. We provide an interface to be able to do that. So I think Juliana will get into maybe tomorrow. Anyway, lots of other methods and many more than what's included here. Very quickly, there's the time module, and this is a way to be able to do things like pause your simulation. And this is built in, so you can say import time. And you can do things like pause your simulation for a number of seconds by calling time.sleep. And this will pause my software for 1 second, 10 seconds, 100 seconds, so on and so forth. You can do lots of other things like timing, taking time measurements to do like benchmarking to see how long something takes. This is all counted according to whatever your computer thinks is the beginning of time, which is called the epoch. That varies by platform. We can skip those details for now, and instead just remember that we can get the current time in integers using time.time. Say t1 equals time.time. The math library, we've already done this a little bit, but the math library provides a lot of basic math functionality. The name is just math. So as we did with square root earlier, import math. Lots of constants defined like pi, not a number, infinity, rounding functions, error functions, factorials, our square root, trig functions, inverse trig functions, so on and so forth. There's a basic statistics package for doing things that will be of interest to us this week, like calculating, say, the distribution of a random walk, quantiles for lots of simulation replicas doing the same simulation over and over and over, and quantifying the variability among replicas, things like that. You can use the statistics package for basic procedures, and then of course, as we may get into in this coming week, SciPy has a lot more available. And with that, we're at 1 minute left on the modules, so I'm going to leave this exercise up. I have a sample code generated for how to do this, but I'd like to just talk you through it very quickly before we start in on questions. This is a classic simulation of simulating a random walk. And so what occurs here is you pick a position as some variable in a 1D space. And so this variable defines a position for where something like a random walker is. And then just do a number of iterations, say 100,000 simulation steps in a for loop, and just generate random numbers at every iteration, and then test a certain probability, say 5%, that the random walker either increments its position by 1 or decrements it by 1. So if that's unclear, let's talk about it via email, which I think everyone has. I'll make that more clear. And again, I'll post the sample code as well. James, I'd like to turn it over to the general discussion now. So I'd like to turn it back to you, maybe stop talking for a minute and yeah, thank you all again for being here and for sticking it out for this very brutal session of crash coursing through a lot of the basics of Python. It's been a real pleasure.